Today we're going to look at getting some common bases and solving some more exponential equations. We talked about common bases in our last lessons, and we're going to expand on that thought a little bit more today. So the first problems we have are to solve each of the following exponential equations by writing each side of the equation using a common base. So for instance, right now in this part A, I can tell you 2 is the base, where that x is your exponent. And our goal right now is to get both sides of the equation to have that common base of 2. So in other words, the question is saying to us, how could we take that 16 and write it as a base 2? What would this exponent have to be in order to turn that into 16? So if I think to myself, 2 squared I know is 4, 2 cubed is 8, so 2 to the 4th power would give me 16. So now since my bases are equal, that means my exponents are equal, and we found our value is 4. Okay, we're going to try the same thing with B. Only difference here is now I have a fraction. So the first thing we need to do is think, how can I write this 1 over 25 without it being a fraction? So in other words, if I said 25 to the negative 1, knowing that that takes it out of the fraction, that's our first step. Now we have to think, how do I write 25 to have a common base of 5? So if I could write 25 as 5 squared, now that's my 25, and don't forget we have that exponent of negative 1. So this brings us to the point where we have a power raised to a power. We know if we have a power raised to a power, we could multiply. So we could say this is 5 to the negative 2. And now I see my bases are equal, which means my exponents are equal. So x has to be negative 2. And our last one, now notice which one has the larger base. The first two, we've always had the larger base on the right-hand side without the exponent. This time on letter C, the larger base is actually on the left-hand side, and it has the exponent. So that's okay. Still works the same way. Anytime you're trying to get common bases, you want to make it smaller. So I want to take this 16 and see, could I make that smaller? Could I make it a common base of 4? So we could say 16 is really 4 squared. That gets me to 16, and don't forget you have again that exponent of x. So we're going to use that same process. Power to a power, we multiply. So this gets us 4 to the 2x, and over here, don't forget that 4 has like an exponent of 1. So that says 4 to the 1st power. So now my bases are equal, and we can set our exponents equal. So I have 2x is equal to 1, and in order to solve for x, divide each side by 2. So I can tell you x is equal to 1/2. Okay, so now we're going to take a look at the same idea, except for now we're going to manipulate each side. So the first round we only touched the one side. Now we have to work on both sides. And again, whenever you're trying to simplify these, probably the biggest thing that you want to keep in mind is always think, make the bases smaller. You don't want to increase. Bases need to be smaller. So if I have to change both of these, which I do in part A, it's not going to be bigger than 8. So I have to think everything has to be smaller than 8. So in other words, how could I rewrite 8 with a smaller number? Well, I know 8 is really 2 cubed. And don't forget we have the x. So that guides me, because now I can think, well, if 2 was the base on the left-hand side, 2 needs to be the base on the right-hand side, and 2 to the 5th power would give me 32. Okay. So again, power to a power, we would multiply. So that really gives me 3x on this side. And on the right side, I have 5. And notice again, I can set the exponents equal because the bases are equal. And if I solve for x, I can tell you x is going to be 5/3. Okay, same thing on B. Make your bases smaller. So I'm going to start with 9, knowing it can't be any bigger than 9, so it's got to be smaller than that. I can rewrite 9 by saying 3 squared. That gets me 9. And then we still have 2x plus 1 as your exponent. That guides me over here to say 27 needs to have the same base of 3, and I know 3 cubed will be 27. Okay, so now we have to be careful with this exponent here. Power to a power we multiply. Keep in mind you're multiplying that entire exponent, 2x plus 1 by 2. And we can set that equal to 3. Okay, so we have to do a little distribution. So this will give me 4x plus 2 is equal to 3. If I subtract over that 2, now I have 4x is equal to 1, which means x is equal to 1/4. Okay, and last one. Okay, a little bit more difficult because now not only do I have numbers I have to reduce on both sides, but I also have a fraction. So I may want to work with this fraction first and get it out of that fractional value. And keep in mind the way that we would do that is by making that exponent a negative. Keep in mind we still have this. I'm just going to work on one side for right now. So that tells me I need to make 25 smaller. And again, I can go smaller by writing that as 5 squared. So now I have 5 squared to the negative 1 to the 4 minus x. So that's a lot of exponents. For 125, so that also tells me it has to be written in terms of 5. So my base here to get 125 is a base of 5. That would have to be 5 cubed. And then again, we have it to the power of x. Okay, so power to a power we multiply. On the left side, I have 3x. On the right side, I'm going to do this in 2 steps. 2 times negative 1, I get negative 2. But now I have to take that negative 2 and multiply it by that whole exponent, 4 minus x. So we're going to distribute. So we have a negative 8 plus 2x. I'm going to subtract over my 2x, and I'm left with x is equal to negative 8. Now we want to see what's the solution set to this equation. Okay, solution set, in other words, is saying just simply solve. So I can't really make 2 any smaller. 2 is as small as that base is going to get. So what that tells me is I need to make 64 into a base 2, because if my bases are equal, we can set the exponents equal. So I have to figure out 2 to the what power? 2 to the 6th power gives me 64. Now since my bases are equal, we can set your exponents equal and solve. So I want to get x squared by itself, meaning I'm going to add over the 3. So adding over the 3, I get 9. I'm going to square root each side, and my answer here is going to be both positive and negative 3. So my solution set for that, I would say I could write it in like a fancy squiggle bracket notation. That would be your solution set. Okay. Now we're going to look at this graphically. So we have 2 exponential curves, and it says they're shown below, and they intersect at point A. And we have a rectangle, it has one vertex at the origin, so that's 0, 0, and the other at A. We want to find its area. So fundamentally, what do we need to know about a rectangle to find its area? Well, we need 2 dimensions. You either need the length and the width, or some people like to call it the base and the height. Either one is okay. Okay, so in other words, I need maybe the base and the height, or I need the length and the width. Okay, so how would knowing the coordinates of point A help us find the area? Well, if we know this, let's think about what the coordinate would be. So we got something like maybe x comma y. So x is going to be the distance from the origin over. So if I know that value, I can tell you that that's the length x. And then I need to find the height, and the height is that coordinate y. So I could say maybe x is going to be the length, and y is going to be the, you could call it the width, the height. Okay, length, we could say either the length or the base. So you got those interchangeably. Okay, so we need to actually then find this. So we have to find the area of the rectangle algebraically using the method of common bases. So we need to go back and look at our equations. And again, I'm going to take note that they're both equal to y. And we always say if things are equal, set them equal. So I'm going to set our equation. We have 4 raised to the x plus 5 halves equal to 1/2 raised to the 2x plus 1. The method of common basis says we need to have a common base between these two. We always want to think make smaller, but we also want to think we don't have a fraction. So I'm going to take this number and take it out of the fraction first. And I know I can write this as 2 to the negative 1. Don't forget the rest of your exponent. So that helps guide me to this left-hand side, saying I could rewrite 4 as 2 squared, and then we still have this exponent x plus 5 halves. Okay. So now that my bases are equal, I can set the exponents equal. Keep in mind, power to a power we multiply. Keep in mind we have to multiply it to each term. So the powers, I have 2 times x plus 5 halves. I'm going to set that equal to my powers, negative 1 times 2x plus 1. Okay. So distributing through, I have 2x plus, when I distribute the 2 to the 5 halves, we get 5. And I'm going to set that equal to, distribute the negative 1, negative 2x minus 1. Okay. I'm going to move the 2x over, so that's going to get me 4x. I'm going to bring the 5 to the side, subtract the 5 over. That should get me negative 6. And when I divide to solve, I'm going to find x is negative 1.5, or negative 3 halves. Okay, so we still need to find the y value. And in order to find the y value, we're going to plug that back into one of our equations. I'm going to take the one with the base 4. So if I take the base 4, I have 4 raised to the negative 1.5, that's what we get for x, plus 5 halves. Negative 1.5 plus 5 halves, that's going, this is 1 equals, sorry, that's going to get me y equaling 4 to the first power, which is going to tell me y is equal to 4. So from a coordinate standpoint, think of what we have. We have the coordinate right now, negative 1.5 comma 4. So let's go back up to our picture. And if I'm thinking of this, we just found the x value is negative 1.5 and the y value is 4. But you have to be careful because that negative, the negative is telling you direction. Okay, so that negative is telling you direction, not distance. You can have a negative distance. So when we go to find the area for this, knowing that it's length times width, I'm going to do this work here, the area being length times width, I know it's going to be a positive 1.5 times 4. And so when we multiply that out, that's going to give me a total area of 6 units squared. And our next one, so we have it, what x coordinate will the graph intersect this other graph? Same kind of idea of like what we just did. So we want to set these two equal to each other to begin with. I'm trying to find the x coordinate of when they are equal. If things are equal, which they are both equal to y, I should be able to set them equal in order to solve. Okay, so again, we have this fraction. So I want to get it out of the fraction, and by doing that, that's going to turn it into 125 to the negative 1. Keep in mind, we still have our other exponent. And now I need to make the base smaller. I can write both of these as a base 5. This would be 5 cubed to the negative 1. This whole thing still to 3x plus 1. The 25x minus a. Okay, again, I can write the 25 as a base 5. 5 squared will get me 25. And then I still have the exponent x minus a. Okay, so my bases are equal. They're both 5. So I can set the exponents equal. Keep in mind we have to distribute this. Okay, 2 times x minus a. And on this side, again, let's simplify these first ones. 3 times negative 1, I get negative 3. and that has to be multiplied by 3x plus 1. Okay. So 2x minus 2a is equal to negative 9x minus 3. And again, what we are trying to find is what x equals. I know we have two variables, but I'm trying to find what x equals. So that means I want to get x by itself. So that means I'm going to pull over the 9x. So I'm going to add over the 9x. That's going to get me 11x. And I want to pull over the 2a because I want to get x by itself. So by adding that over, I get a positive 2a minus 3. And now in order to get x by itself, divide each side by 11. And I'm going to find x is equal to 2a minus 3 over 11. And since we just had to find the x coordinate, we can stop there. Okay, bring any questions you have to class and we will work it out. Have a great day.